I'm evil. Oh no, this keeps happening. I don't know when I typed emo. The toggle for my evil mode is emo, because it's different than my horns, which I think is evil. Yeah, my horns are evil, but the other one, oh, I can't turn them off. Oh, they don't want to turn off. Well, okay, I guess I'm stuck like this. But yeah, if I type emo, I turn emo. Hey everybody. Sorry for coming in all emo, like. I am very excited. We get to do fun stuff. This out of here. This isn't right. No, we're gonna do some differential analysis, which is super exciting. Saying a lot. Don't worry about it. I'm trying to think, so when we were doing this, not this problem. Did I do this other one on stream? I did this one on stream, I think. Yeah, so I was asking my professor, I was like, oh, so I understand that, well, first off, he was like, yeah, so there are two ways you can do this problem, because if we remember, the problem was like this, and there's this internal energy change, right? And I was kind of like, well, we have T1 and T2, and we can find the specific heat, the specific, whatever, volume one. I was like, why would he give us this to, like, plug in? Like, then what are we solving for? And I asked him about it, and he was like, yeah, so you can do this problem two ways. You can either do it with the first law of thermo, or you can just instantly do this. And I'm like, I mean, okay. And he was like, I'm just asking for the internal change in energy. I'm not saying that you have to do it a certain way. And I'm like, okay, I thought you meant you wanted us to, like, prove that this was true or whatever. He was like, no, you can just instantly do it. I'm like, okay, I guess. Like, he was like, why would you want to do more work? And I'm like, because I want to get better when I can't just do that. But so we don't actually need to substitute that in. What we need to do is, I just forgot a term, and then everything went downhill from there. So I'm gonna redo this really quickly. This shouldn't take too long. The yellow things are the notes, so, like, he said I should write out the first law of thermo, like, totally, and then start crossing stuff out. And, I agree with him. There are just some things that I skipped in this line. I was like, well, the gravitational potential energies are going to cancel out because they're going to be the same. So, I did that in my head, but we gotta do our due diligence here. If I can get my lasso tool. Okay. I'm gonna move all this over a little bit so we can fit that work term in. Because the reason I didn't draw the work was just because we don't have any work on our schematic, or I guess it's not really a CV, it's a schematic or whatever. But we'll just say plus W in out of here. It goes 0. We don't have any of that. Okay. Then we can rewrite this properly with the correct terms. As I'm going to write out all the energy. So we'll do CS1 plus E1 squared over 2. Oh, the other thing was, I said assume constant properties because I didn't want to say, he also said I don't need to do this, which I agree. I don't actually need this. I'll just cross it out so we know that I had that before. And I was saying, like, I didn't want to write properties and velocity, so I was just like, well, it'll cover it. And he was like, no, you need to write constant velocity. I was like, okay, I did think about that. I know that I have to do that to get it out of the integral. I didn't do that. So we got that in there now. Oh, let me pull up me when I don't have my stream manager up. There we go. We got that. So v1 squared over v2, or no, v1 squared over 2 plus gz1 plus u1, and that's all plus, I just want to take stuff out of the integral already because I don't want to rewrite the entire thing. Okay, we're not going to rewrite the entire thing. We're going to pull out some stuff because we do know there are some constants. Like we can pull out so we can pull out negative rho 1 v1 And I can pull it out as a v1 because we said that it was constant over the surface. And then we have p1 over rho 1. And this whole thing is dA1. And then we have this basically the same thing. So p2, v2, cs2. I'm just going to switch all the 2's. v2 squared over 2 plus gz2 plus u2 plus, that looks like a v, e2 over. So we want to solve for the internal energy change, which is cool. We can do that. Okay, so we got that. What's next? Let's see. Split up the integral? Let me try and turn off my emo now. Oh, my emo went away. And good. I'm back to normal, normal self. I think I had a cooldown on it or something, so I couldn't turn it off. Okay, so we split up this integral. We're gonna get negative rho 1, v1. I'm just gonna integrate each thing. So v1 squared over 2 times a plus gz1a. Now, I think I can say u1a. I might not be able to say that. I'm gonna leave u1 as an integral for now. But we know that u1 is a function of temperature. So we said temperature would be constant across, so we probably can pull that out. But and then pressure 1, so p1 over rho 1 a 1. Well, the a is the same, so I'm not gonna say that. So we have that, which is good. That's there. I'm trying to remember what we're solving for. But let me write this one out too. We're trying to solve for, we're trying to get the u1 minus u2. But my issue was, and I think my issue still is, oh no, you know what it is? Okay, yes, I remember, I'm so remember core. Okay. This is okay, actually. No, we'll leave it like this. I'm gonna, I'll leave it like this for now. I think it should be okay. There's one specific thing, so my issue is I was saying like, I'm gonna say z a so that we can cross these out. That. Did I say v1 equals v2? I don't think so. Did I? Yeah, it doesn't because the densities aren't the same. Okay, good. I want to make sure I can't cancel that out. Did my due diligence. My issue is I had these properties that were different, right? Out at the front of these integrals. e1 over rho 1a. Right, these. And I was like, I can't, like, the velocities are different. And the densities are different. But you know what's not different? Q. And that's what you have to do. You have to factor out like this. So, not Q dot, but Q specifically. So, if I do this right, I'm gonna pull out this. We're gonna see negative Q. I mean, I could say like CS1, U1, dA1. It doesn't really, I can pull that out of the integral probably, but I'm just gonna leave it. We're gonna pull out that negative Q, like this. And then we're gonna add them together. And that's what we're gonna solve for. Actually, I might as well just put this on the other side. I'm gonna move everything over, so we're just kind of going like this, and I just mirrored it. Alright, so what do we have on this side? We have, well, I can factor out, there's still a Q. So it'll be, we can do this, we can say, So we are moving it to the other side. So it'll be if I do a positive Q, when we move the negative stuff will be positive. So it'll be V1 squared over 2A plus E1 over rho 1A minus V2 squared over 2A minus P2 over rho 2A. I can factor out an A. I'll do that. Here we go. And then we just have to say, essentially, like, delta. So if it's U, wait, no, I goofed something. There's a minus here, I think. If it's a minus Q, yeah, that would be a minus here. I think we want that to be a minus like this. So it'll be like delta U equals negative Q out over the flow rate. That's our head loss. Head loss. And then plus A V1 squared over 2 plus P1 over rho 1 plus minus V2 squared over 2. I could probably consolidate this more by saying like V2 is in terms of other stuff. Oh yeah. And so that's all the stuff that they gave us, I think. Or at least the stuff that we can find. Like, I think they didn't give us V2, but I think we could find it. Oh god. Why did I do that? They gave us the rate of heat transfer, so that's our Q. Oh wait, I don't need to deal with head loss, sorry. Although that is... It's not exactly head loss. That would be head loss. Kind of. No, it wouldn't be. It would be work. Would it? Don't look at me. We're not doing pipe flow analysis yet. It's similar to. It's similar to that. Okay, we're gonna switch gears. How long? That was pretty good time. That was pretty good time for any problem out. All right. Now we get to do math. It's like all math. Alright, so this is differential analysis. We were doing integral equations before, which was sort of like a net effect. Sort of like how you sum forces in statics or something. You're not really going to be getting details about, like, you know, a field of forces. You're just getting like the overall force. And so in fluids, when you're doing your integral equations, you're getting just that. You're getting an overall picture, where sometimes you want to actually know exactly what the velocity field is at a given point, right? Or at any point, really. And so for this problem, we still use a form of continuity, and we also use linear momentum conservation, or linear momentum equation. Hi, oh my gosh. Fluid flow, right up my alley. Oh my gosh, I love fluid flow. It's super fun. It's like, well, and I actually get to do math. We get to talk about curl, finally! Somebody uses, like, actual multivariable terms. Trying to learn it with the goal of simulating it? Ooh! There are some, oh my gosh, the other day, we were, at the end of the stream, we just went through, like, a bunch of, like, fluid simulations, and it was really fun. I really, really like fluid dynamics. Heat flow simulations last week. Ooh, that's awesome. We don't really do CFD or like the computational fluid stuff at this level, because it's a little bit more like, the goal of this is to simplify problems enough so that you can solve them by hand instead of having to solve them with a computer. But I kind of wish we did a little bit of computational stuff, but I mean, the prerequisites for this class is like not higher level differential equations. Yeah, we're gonna do conservation of mass. Which I should remember how to write that one. It's something. It's like it's not the total acceleration one. I know Navier-Stokes off m equals m. Well, yes, you're correct. But we gotta take some partials. Let's see. Where are my notes? Where are my notes at? That's Bernoulli. I mean, I'm pretty sure we're getting to the point where we can. My mic does that. I'm so sorry. We call him the mic demon. I have to like clean reinstall. I'm so sorry. We have to clean reinstall. Like, I'm gonna clean reinstall my entire OBS when I get home. It doesn't happen on my PC though. It only happens on this computer that I stream on most of the year. Don't know why. Don't know if it's a grounding issue. Don't know if it's just software, but it bypasses all of the noise filters that I put on also, which I don't even know how is possible. Like, I put a limiter on it and it just doesn't work. I think I'm making an OBS game? Ooh, that sounds cool. Incompressible, so we don't have a changing. That, which means that we get del.v equals 0. Gonna fight with OBS trying to do challenges for an audience? Ooh, wait, that's awesome. What kind of challenges? Sounds super fun. I love quirky stream things. I'm gonna try and get into. I want to try and learn Godot because I saw one person make a stream overlay with Godot and I was like, that would be so cool. Godot. I've heard a lot of good things about it. I streamed some Godot. Ooh, wait, oh, you stream? Oh my gosh, I gotta check out your streams. EU, dx, dv, dy, plus d, w, dz. I think. I'm gonna use it to make a presentation for a local garden club. Oh my gosh. That sounds lovely. That's 0. 2D flow. We're assuming that it's that. So dud, whoops, that's a u. dudx has to equal dv dy. Now we just gotta do that. So dv dy equals... okay. Gonna be 3x plus 1x squared. Wow, how nice. What is w in this context? Ah, so for, at least for this type of fluid mechanics, we have 3 directions for our velocity field. So we call the x component or the I hat component u, and then we call the y hat component v, and then w is the z component of our flow. And so they specify in the problem statement that it's 2D. And if they're asking us to find the x, I mean, for me, it's like, I wish they would have specified that it's 2D in the x and the y, because technically you could have it in like the y and the w and it wouldn't matter. But yeah. Probably put an assumption. I think I wrote an assumption. I did. I wrote a little face on dpdx equals 0. It's not true. That was when I was doing the wrong thing. But it's okay. It was me trying to use something that wasn't the conservation mass first, and you never do that. You always conserve your mass. And then we just say, so du dx equals 3x plus 1x squared. And so x, we integrate these. Well, let me separate it, I guess. That'd probably be smart. Don't know why I'm writing 1 out of here. Okay, there we go. Nice little integral. What do we got? U equals 3x squared over 2 plus 3x cubed over 3. Wait, but why am I... Don't know why I put a 3 there. There we go. Nice. Easy enough. And then we just have to do the cross product to find if it's irrotational or not. It's just the curl. I wish they would teach, like... They don't really teach us things. Which is funny. But... Like, they briefly talk about curl. But, like, not really. I just studied this. Curl equals 0 means irrotational? Yeah, exactly. Wait, what, are you just doing it for fun? Or are you, studying engineering or physics or... Yeah, and if it's irrotational, then we know that it's also, what's it called? Incompressible. Wait, no, it's, not incompressible. It's, inviscid. I'd like to go back to school for my master's degree, so I'm learning all things again. Oh, that's awesome. Oh, that's so sick, yeah. I really like fluids a lot. I think it's fun. I wish that it was a little bit more rigorous, which is funny because I think a lot of people would say that this professor that I have is one of the most, if not the most, currently, like, rigorous professor, because the rigorous professors that he learned from, like, retired, so they're, like, too old to teach, but they were, like, some of the strictest, but I'm like, this is kind of, like, not that bad, really. It's just fluids. It's just fluids. I'm trying to remember if it's, I think it's del cross? Yeah, 1/2. Or it's, the general is just del cross v for our overall. Okay, so we have... There's a nicer looking way to do cross products. I feel like there is, but I don't... It's just fluids. I think my DiffyQ professor said that once too. Well, I feel like as long as you break anything down into small enough bits, then it's not too scary. And I think that's like a big part of fluids. I will say it also helps that like a lot of the math that you're using is not actually hard. Like, you know, differential equations that I tend to come across, you know, we had to learn like a bunch of really nasty like sine and cosine functions and all that stuff, but you don't really use those until you get to like controls or you know, more complicated sort of system type stuff, because like you're not going to be using like a delta spike function to like describe a fluid mechanics thing at the beginning. You're going to be doing like, here's a 1D flow, here's a 2D flow, like, and it doesn't go higher than, you know, 3 dimensions. So I feel like the math is hard, and then no, that's just chill. I think there was I remember learning a way to do this. It's vague. I took multivariable a very long time ago, but I was like, I think I remember my professor mentioning a way to do this quicker. Well, not quicker, but just like to remember how to do it. It's not particularly tricky though. DUDZ. There's some. It might have been like chain rule stuff though. It might not have been this. Let's see if I can do this. Is that right? DU DY. You can also just think about it as moments. Like that's what I think about it as. And I was like, yeah, that's right. Yeah, we're good. I mean, it's really not that. Oh wait, now we have to do it though. I guess I just have to check if in all directions it's 0. This is definitely like a chain rule thing. This is like in my brain. I'm like, there's something I did in multivariable where you had to take the two partials and see if they were 0. I don't remember if that was solving partial differential equations. It was like there was a check that you had to use to solve a particular kind of differential equation, I think. When you organize cross products this way, is it different when you put ijk across the top column? No, so I'm using column vector notation for all of these. So I'm writing my vectors, instead of writing them like x, y, z, I'm writing them like x, y, z, because in math, you're gonna write most vectors like this. And so I always write my cross products like this, but one of the rules of like determinants is that you can take a determinant like across any row or column and it's going to be the same. So yeah, the only thing is this is negative actually. I got that. I flipped that. And then I'm just writing the vectors like as, again, I'm writing them as. So this would be like so I'm just doing this, what is it called? Wait, oh, I did that wrong. Lol. It's called like the, adjoint, I think? I was thinking about that negative. Yeah, that's just me being goofy. This one is also not right. Lol. That's, dwdy is d. It shouldn't have any, let's see, this one shouldn't have any u's in it, this one shouldn't have any y's in it, and this one shouldn't have any w's in it. Yes. Yeah. Yeah. I would have maybe figured it out when I got that it was rotational, and then I would be like, I did something wrong. Alright, time to just do... Okay, dw is 0. dw dy is 0, because w is 0. Minus how much y does it change? How much does y change in the z? None, because the z doesn't exist, kind of. How much does w change in the x? Doesn't change at all. How much does that change in the z? That's also 0. And then how much does y change in the x? We'll figure that out. dv dx equals... Wait, I did that one already. Oh, no, I didn't. It's gonna be 3y plus 2xy. And then du dy equals... What did I say? Let's see. 3x squared over 2, so it'll be... Oh, wait. There's some y's in here that I'm missing. What are we doing? What are we doing, fellas? Let's see. dv dy is going to be that. That's correct. And then... What term? What's up with that? Again, that right? Maybe it's not dv dy. Let me think. If I was crossing it or dotting it, it would be... Yeah, it should be matching that. So that... Well, there's a negative there. There's a start. Maybe that will help. Probably not, but... if it's negative, yeah, that should be fine. I'm sorry. What I was saying was, it might be irrotational, because it's okay if we can't use Bernoulli's. We can still use, so this is a, if we assume that the flow is laminar, which, I mean, we're given a component in the y direction, so like, it's probably laminar. And then if we assume that it's Newtonian, then we can use Navier-Stokes. And we don't need to, you know, use Bernoulli's equation. Bernoulli's equation would hold if it's irrotational, because it'll be inviscid, but it's not required. We could also, we know that it's, we can't use Euler's, because we'd have to say that it's inviscid. So, but we could use Navier-Stokes if it is irrotational. Let me just like pop this into a cross product calculator. Or would be the easiest way to do this. Let me think. I could probably want to make sure my partials are right. That's silly, because it's very simple. I don't think it's wrong, because I think, let's see. Sure. Always good to check. We would have, okay, D. Oh, no, this is this. And then the negative would be there. Going slow. So we need dv udx, yeah. Oh, we need to integrate this one. This is our negative 3x plus 1 minus. Gonna be okay, good. I can still do basic integrals, and then I just need to take the partial of that. With respect to y. It's only x's. It doesn't have any y's. I don't know why I'm like freaking out about this. I don't think we can use it. I think you have to use. Navier-Stokes instead, which you can do. It has pressure in there. You would just be solving for. I mean, it wouldn't be that bad. A lot of your terms would be 0. Maybe we could try it later. If there's not another pressure one. Not equal to 0. 0. Lol. So this is not, it's rotational. Rotational. Not inviscid. There's friction, essentially, because something is rotating. If we have fluid elements that are deforming like this with angular deformation, that's the sides of our fluid element are rotating, and then that means that that's due to like shear in some sense. And so it's not inviscid. Can't use Bernoulli. I mean, it would be nice to use, well, actually, that kind of makes sense, because if we're trying to solve the pressure field, we wouldn't be using Bernoulli anyway. Bernoulli gives us information about a difference in pressure, and it's still differential analysis, but it's not, it is not a field. It is information about points. Okay, let me grab another one. Let's see. I think the next one is about, I don't remember. I kind of want to do some, we were doing dimensional analysis today as well, and that was pretty cool. I was like, ooh, this is exciting. Ooh, we get a plot, we get a tennis ball. This is a good problem. Or we have to make a plot. It's very small, don't worry. Here we go. Okay, an incompressible, inviscid fluid flows steadily. Okay, probably Bernoulli's. What even is dimensional analysis? Dimensional analysis is, it's a tactic. So like, if you have, you're trying to experimentally determine something like, let's say you have a pipe and you want to determine the difference in pressure from one end of the pipe to the other end of the pipe. and trying to figure out like what variables that you might need to change to like correctly define this function. And so it ends up being a function of like 6 variables, probably. Like, you know, the length of the pipe, the diameter of the pipe, the viscosity of the fluid, the roughness of the pipe, the velocity of the fluid, and the density of the fluid, right? So you have all these 6 variables. And if you want to test this experimentally, oh gosh, hi Clem, you would have to do 10 to the 6th experiments if you wanted to do like 10 experiments for, you know, the length. Or, you know, let's say you even just did 3, that's still 3 to the 6th. It's a large number of experiments. So the idea is you want to be able to combine variables into each other, where you want to find variables that are essentially like linearly independent and ones that you can smush into other variables. So you can say like, you can essentially get this down to using a certain method. You can say like, okay, well we're gonna choose ones that are important, and it's gonna be like velocity and density and the length of the pipe, or and the diameter of the pipe. And then you have only 10 to the 3rd, 1,000 experiments to do instead of 1,000,000 experiments to do. I'm sorry with Prime Gaming, they've been subscribed for 2 months. I'm so special. Okay, maybe now to leave me alone. I want to see if we might be able to do an example. I'll try and throw an example in after this one, because I want to mess around with it a little bit. It's really cool. You make like a table of orders of magnitude of stuff to put together and find nearly independent stuff. It's cool. It's like a little bit of matrix stuff too. Okay, so we've got incompressible, inviscid, steady flow. Cast a tennis ball of radius r. According to more advanced analysis of the flow, the velocity along the streamline, okay, we get a streamline, probably Bernoulli. AB is given by, okay, so we have a stagnation point at B. That's where our flow is going to go to 0 at the end. Every time I open up your stream, I'd nag me to share. Anyways, hi, math time, yay. Oh, I'd like to see, but I'm half lurking. I just got done with community garden work and I'm pretty whipped. Oh, yeah. Don't worry about it. I'll be here. I need to do a craft this for sure, but I finished my day. Wait, I need to do a craft to this for sure, but I finished my daily craft. Maybe I'll do comm work. Oh, yeah. Dude, Wait, I can show the comm that I'm working on. I think. Is it up? It might be up. This oh no, wait, Ethernet's up. Yes! New Ethernet art. I was thinking about how to draw. It's so hard to draw lines extending their necks without them looking really stupid. They look kind of like seals. Like, their necks just like pop out, but I gave them a big cape. That's not what I was doing the comm for though. Where's my comm? This is the comm that I'm working on. I might color it. Oh my gosh, that's so awesome. I know, it's pretty awesome. I was so happy. I was like thinking about this. I was like, how do I make him look intense? Because like it looks intense if he's moving, but if he's just standing there, he looks kind of stupid. So I gave him a big cape on top of his other cape, which is just his body. But yeah, this one is cool. And then I've been doing all the little details. I know I got to greeble him, which was very fun. So VO is our upstream velocity, and then my music got paused. And then derive an expression for the acceleration experienced by the fluid particles as they flow along the streamline. Note, you are only considering the flow along AB, not the entire flow field. In fact, you do not have information about the entire flow field. Having understanding of what a streamline is will be helpful with this analysis. Okay, we need to think about what is acceleration. Okay. Well, there's an equation first. Off the top of my head, I do know that it is our time-dependent acceleration, which, if we take a look at our little velocity that we're given, we don't have any time-dependent acceleration. It's a steady flow, also we know that. And then we have our locational or convective acceleration, which is as we move along the flow, does our velocity get bigger? And if we look at our x component here, as x increases, well, as x is going to be getting smaller because I guess x and y are the back of the ball, sure, or not the side of the ball that we care about. As x is going to be getting closer to 0, and so our velocity is going to be, wait, that doesn't make any sense. No, okay, a is our origin. That's a weird way of saying it. Our velocity is going to be decreasing, so we're going to have deceleration as we get closer to the ball, that stagnation point, which, if we think about it, at x equals our stagnation point, we should have 0 velocity, or close to 0 velocity, depending on how close that thing is to where we are. Oh yeah, because x will be r in that case, and then it'll be r over r, and it's just VO, I guess, not 0. What am I looking for? I'm looking for my acceleration equation. I'm just gesturing into the air. Total derivative. Here we go. Okay. So before I start doing this, actually, I think we should do conservation of mass, because we always do conservation of mass. Why not? We could do it for fun. I mean, not for fun, we should do it. I don't really need to assume much because they give us a lot of stuff, but we'll see if we need to assume anything. Okay, so conservation of mass. Kind of funny to do because we are just going to be jumping to other stuff, but we're going to have 0 equals d rho dt plus rho dot that is not rho, del dot rho v vector. And this is an incompressible fluid, so we're just gonna pop that. And we're gonna get 0 equals del dot v. So we know that du dx plus dv dy plus dw dz equals 0. And let's just check. So this is... We don't really want to, I guess, assume anything else about the field. We don't want to say, like, well, dw is 0, because it probably wouldn't be 0. But we're just not gonna look at it, so then it won't exist. That's the way I think about it. Then we're gonna do I don't know why I put 4. He doesn't have 4. So I think we're just gonna start with Navier-Stokes. I mean, I could potentially... Wait, no, what am I doing? I need acceleration. Acceleration. I just got too excited. Guys. Okay, acceleration. A equals big D dv dt, which I think is a very funny thing. I don't know if that's a thing in math or if that's just a thing in physics, but just the fact that they're like, we need a derivative of v, but we need it to be bigger. So let's just make it big D. Like, we need the total derivative. It's big D instead of small d, and even tinier d. We got big D. I feel like it's like illegal. I feel like they made that up. But that equals dv dt, which is going to be 0 for steady flow, plus v dot del times v, which is going to equal okay. One thing that was very interesting is I don't know why I wrote it like this. I have it written like this, so it's, I mean, I know it's different, but this is a good learning opportunity. They don't really teach us del so del's an operator. It's a thing that exists that like kind of houses these derivatives. But they don't really teach us it. I mean, okay, they kind of do. But I also took calc for multivariable like a year plus ago, so it's a little bit out of my brain. But also, I'm going to be real, I don't think my professor, who I almost just name dropped, I probably shouldn't do that. I don't think he taught us it, but that's fine. I don't, let me look up why these two are different. Why is del dot v not v dot del? The dot product is not commutative. I feel like the whole point of the dot product was that it was commutative. Like, let's see. There are frustrating abuses of notation in Griffiths. Professor Wilkenstein. Yeah, Professor Frankenstein, actually. This is, like, this is an EE book. True, finding a digestible treatment of all the derivatives, grad, curl, div, Laplacian, and various coordinates is hard to find its level, so the inside cover is your friend. Well, okay, that... Okay. Del dot v and v dot del are two different mathematical operations. Del dot v is the dot product of the vector del and the vector v, while v dot del is the dot product of the vector v and the vector del. Okay, but is the dot isn't... Wait a second. Isn't the dot not... Is the dot product... I thought the dot product was commutative. We do that all the time in inner products. Yes, it's commutative. What? What stream did I find? Hi, I'm Damie. I'm a cat boy, and I do engineering things. Oh my gosh, hi Cosmo. We're doing fluid mechanics right now. And I'm trying to figure out why people are saying that the dot product is not commutative. Is the dot product of nabla? What? Because I never actually... I'm gonna say it's probably because it's just del that it's weird, but like, I would like to know why. How does del act in dot products? They're intuitive? No. No idea what that means, but I'll stick around. It's okay. Like, I think maybe 80% of the people who watch my streams have no idea what's going on, and it's okay. The reason people say that actually is 7, the number 7, that's why it is the way it is. I solved it for you. Thank you, Cosmo. That makes so much sense now. Wait, what the? Why did it change my search to how does Dally act in dot products? Who's Dally? It's okay, Steph, most of Davey's viewers are not math heads, me included. Yeah, it's okay, I love you guys. I do other things than only math. Okay, but why does the dot and cross product give you divergence? Matthew Johnson, YouTube video. How is the dot or cross product possible using the del operator? Has no value of its own, as it's an operator, so it can't be called exactly a vector. But in vector calculus, we see that divergence is the dot product of del, and that is not phi. What is that? Is that phi? That's phi. Never mind. Listen to me. I want to study physics in the future, but I don't know what exactly. Oh, that's awesome. If you ever want explanations of what I'm doing in layman's terms, I am very much totally down to explain it, because all of this stuff is really quite like straightforward, as long as just like doing the math is hard. Divergence? Wow, this is just like that book series that ripped off Hunger Games. I love... Okay, I really... You guys don't understand how much I love certain math terms. Like, I love that if you take... So, you know, like velocity and acceleration, right? But you can go farther than that. If you go farther than that, you get jerk. And you can also get curl and divergence. There's so many good names for just like derivatives of stuff. And it's just really funny. Okay, the del is not a value vector, but a vector of operators. Okay. The divergence of a vector field is not a genuine dot product, and the curl is not a genuine cross product. Del dot A is just a suggestive notation which is designed to help you remember how to calculate the divergence. Oh, jerk? Yeah, it's called jerk. The third derivative. The notation is nice because it looks like a dot product. Oh. Divergence is an operator which eats a vector field and spits out a scalar field. I love Stack Overflow. Curl can be defined similarly. It's a pain to write out in its entirety. Okay, so it's not actually... It would be more accurate to say that we're just finding the curl or we're finding the divergence. I'm jerking it and diverging. She jerk up my acceleration till it diverge. Me, except it's inviscid. No jerking happening. Zero jerk. No friction. I don't think you can jerk a fluid, an inviscid fluid. You jerk on my curl till I diverge or something. If it was inviscid, it just wouldn't move. Make sure you're not accelerating too fast. Yeah. Wait, okay, I'm trying to like think about this. Okay, this makes sense, but now I like don't know how to calculate the divergence. Oh my gosh, 3 blue 1 brown video? React Andy time? No, I can't watch 3 blue 1 brown on stream. He's too cool. Calculate or divergence operator. Stay in your lane of your state of inertia. So true. Divergence is a vector operator that operates on a vector field. So divergence of f is del dot f equals... Okay, so essentially in one of these we're finding the divergence. This is not divergence. But what I don't understand is then I think this is divergence and we're multiplying this times this. So why isn't it written as... Wait. No, I got confused. Jerking at nothing style. The fact there be no movement at all. Yeah, so like an inviscid flow means that there's no friction. So the condition of a fluid is if you have like a fluid here, this is just like water or something, and there's a plate on top of it. The fluid at the top of this is going to move at the same speed as whatever this plate is moving at. And so that happens because of like friction, right? And then the fluid down here, if this is static, would have 0. So you end up with a fluid that kind of like shears as it moves, right? But that only happens if there's friction. So if you didn't have friction, it would just stay there, jerking at nothing style, exactly. This would just go. This would just be over here now, and the fluid would just stay exactly there. That doesn't really happen, obviously, but... Oh. Yeah, not really great for jerking it. Or maybe it would. I don't really... I think we need to do a more complex analysis on that, actually. We'd have to run some experiments. What's the lowest... Water is pretty low viscosity, which means that it has, like, low shear and stuff like that. This is making me insane. I'm trying to think about... But it's also, like... Is it because it's, like, V... Is it... My brain is trying so hard to understand and see it. Whoa, Damien. In the fluid. Straight up jerking it. And by it, let's just say nothing. I'm trying so hard to understand why. What is this? This is, Guys, it's okay. I'm coping really hard. Wait, maybe the textbook. Okay, we're gonna go to the textbook. The textbook's gonna be like, do it. Like this, and they're not gonna explain it. It happens every time. It's like the Charlie Brown football scene. I go to the textbook. It's like, oh, are you gonna have the definition? Are you gonna have it actually in math terms? They're like, yeah, we're gonna have it in math terms. And then they just grab it out of my hand. They just go do cross product. Can you explain all the letters? Maybe we'll come to a solution and enlighten me as well. Sure, I can do that. Okay, so there's a lot of letters. There's a lot of letters. Okay, so where do I start? All right, basically in this analysis, what we're doing is we're doing two things. Okay, so this is the problem, by the way. We have a tennis ball, and it's in some fluid, and we know some stuff about that fluid. So we're given the velocity of the fluid along this line. And so it's asking us to find the acceleration of that. So we know that just kind of from our prior knowledge, or maybe just like colloquially, we know that like acceleration is going to be like the change of velocity, right? So we're going to have to use some calculus, probably, and do some derivatives of velocity, because the derivative is just a rate of change. But I mean, you know, it's still just a rate of change of this thing. So what we start off by doing is saying, whenever you do any fluid problem, you want to say, you want to relate velocities at different places to each other, because you don't necessarily have a lot of information about velocity. In this time, we might not actually need to do this, but it's just a good rule of thumb, essentially. And so what we're going to say is that if we imagine we like draw a box around this, all of the mass coming into the box has to go out of the box somewhere. So it could go out of the box here, could go out of the box here, could go out of the box here. So this is called conservation of mass, because we can't just destroy mass, just like we can't destroy energy. It has to go somewhere. So we start by doing the conservation of mass, and that is this equation. This is the general form of the conservation of mass in differential form, and it looks kind of scary. There are a lot of things here. It's okay though. I can explain it. Okay, so rho, this fancy P here, that's density. Okay, and when we're working in fluids, we can't really put like mass in things. Like if we're doing, you know, like statics or something, or if we're doing just kind of basic physics, you know, we might say like F equals ma, because our object is like a box or something, and we know how much mass that has. But for a fluid, fluids kind of go all over the place. So we can't really use mass. So a lot of times when you see density in fluid problems, you can think of that as like a replacement for mass. So essentially what we're saying with this is we're saying that if I were to move this around, we have to say that the change in mass of time is equal to, and that this term on this side altogether is equal to the change in mass in space. So I'm going to put it back to this. So like the change in mass of time is like, maybe we have a fluid that can be compressed, and so as more fluid enters that box, it compresses into the other fluid, and like air, right? Like if you kind of pressurize it, right, you can like squish more air in there. And so that's why we might have a density term like this, the change of time. And then for this one, this is talking about the actual space of our box. If we're thinking about our box, like we're kind of keeping track of how fast each little piece of mass is going in that box, so we can kind of follow it. And so we're saying like, okay, if it's moving faster over here, it doesn't, this term is kind of keeping track of like, okay, it's moving faster over here, it's moving slow over here. So like there's going to be, you know, more or less mass like moving through here. And basically all those things have to add up to equal 0. What is the triangle there? Oh, okay. Okay, we're getting there. We're getting there. That's the math part. Davey, I want you to know your streams are so delightful. You're the only person that make me laugh at a fluid dynamics joke when I know nothing about them. You do know about fluids, though. We live in a fluid all the time. All right. Okay. So now for the details of this. Okay, this thing is an operator. We live in a fluid all the time. Yeah, air. Air's a fluid. gases and liquids are both fluids. So this is an operator. It's called del, like del, D-E-L. Oh my gosh, thank you for the follow, by the way. I'm looking over at my notifications. So this is what I'm like mulling over right now, but essentially, del is an operator that does a specific thing to a specific function if you write it a certain way. That's kind of how like all higher math stuff works. Isn't delta written upside down? So this is delta, which is a change, but del is a different thing. This is also sometimes called the gradient, and what it represents is actually a vector of the partial derivatives in each direction. So if I wanted to take the gradient of a multi-dimensional function, it's basically like saying how much is it changing in the x direction, how much is it changing in the y direction, how much is it changing in the z direction. It's like a package of all of our rates of change, essentially. But they're kind of split up into each component so that you can work with them. So that's the reason we have that in here, is because our space isn't always one-dimensional, right? If it was only one-dimensional, we could just say that this was a derivative, right? The change of velocity over like a line or something. And in this case, we do have a line, but it's a little more complicated than that. So we have if we have a two-dimensional space here, we have to be like, it's like a big delta. Exactly. Yeah, it's like, and that's kind of like this big D idea as well. It's like you have something, but now let's have more of it. So what I was doing here was, and then, rho is just going to be a constant here. That's still our density. And then we're operating, really what we're doing is we're operating on this, right? Because if this is a dot product, we can pull the constant out. It's kind of not a dot product, which is why it's like kind of crummy. But so that's what we're doing there. And essentially what I did was, we can say that this is 0 because it tells us that it's flowing steadily. And this is a little bit, again, we're like going hyperspeed through like 7 weeks of fluid mechanics right now. But essentially steady flow is when you have, if you have like a box, we're gonna think back to our box. If you have stuff going in, the stuff going in is at the same rate as the stuff going out. So it ends up with having a picture that looks the same all the time. So if you can imagine, if we started slowly adding more stuff here, this velocity would, there would be more mass in there, right? And our picture would be looking different. But if it's always the same, the velocity in here is always going to be the same. And so that's our steady flow. And that basically means that we aren't changing at all with time. So if we have a time derivative like here, well, we have a steady flow. So our density is not changing with time, so we can bring that to 0. And then I just factored out that rho, and because, it's a constant, we can, so it won't accelerate. You're getting somewhere. That's a good point. There is going to be a part of acceleration that doesn't exist for sure. But there's some interesting behavior. So like I think the best way to describe this is, let's say you have a nozzle. Okay, so a nozzle is meant to accelerate flow. That's what its job does. It speeds flow up. So we have water coming in here. Here we'll do fancy water. And we have water coming out. Now this can be a steady flow problem, but the fluid is going to accelerate. And that kind of sounds crazy. But so the fluid's coming in with some velocity here, right? And as it goes through here, we know that the masses are equal. So there's a lot of mass over here, right? Big mass. And there's a little bit of mass over here, right? Coming out of that, because it's due to the area. So to make the big mass equal the little mass, right? Or make the little mass equal the big mass, this mass has to move faster to get out of the way, essentially, to keep that mass conservation happening. So what it ends up with, right, is you have this little velocity here all the time, and you have a higher velocity over here. Is it F equals ma? You can use F equals ma to talk about things. This actually isn't F equals ma. This is like a pre-F equals ma thing that we generally tend to not talk about when we're talking about systems. So generally when you're solving a typical physics problem, you actually don't do this idea of conservation of mass. So F equals ma is like a conservation of, maybe not conservation, but it could be like examining like momentum, right? Or examining energy, right? Those kind of things, and forces are momentum. But because if you were trying to do like conservation of mass on, you know, like your system that's a block, it's like, yeah, the block isn't changing. Okay, check box. Like you can write like, okay, m.1 equals m.2 for a single box, and they both equal 0 because there's nothing is going in, nothing is going out. So it's like a pre-step that we have to do for fluids, because when we're tracking fluids, they're moving essentially all the time. And if we were trying to track, like, we could say, you know, let's just follow a little piece of mass through this whole field, but that would be so hard to keep track of. We don't know, like, where this little thing is going and what it's doing, you know. There are reasons why we might be interested in, like, a particle. Okay, but the fluid has to move. You've now been indoctrinated into the group of people who have heard my mic explode. I'm sorry. And metal pipe. I thought my headphones were dying. Nope, that's just me. That's just me being haunted by a demon. Anyway, conservation of mass. Okay, so we have this thing where we'll talk about that in a second. Okay? We still got to finish just the regular conservation of mass. We have this, and then you can rewrite this. This is just shorthand for writing this. So I didn't actually do anything with this yet. We might not need to use this, but I just have it here because we're saying that the change in the x has to equal the change in the y has to equal the change in the z. Okay, so now we get to acceleration, which is what we're trying to find. So this is an equation that exists, and what we're doing is, generally when we would take acceleration, we would take a time derivative, right? And you pointed out earlier that that time derivative would be 0 because we don't have a change in time, which is exactly true. It's a steady flow. But we do have that idea of there are changing velocities that exist in a steady flow, right? Because our area is changing, or in this case, right, like there's the ball has these forces of just existing in a space. It's going to be pushing against that fluid, and it's going to be changing its velocity, right? I left for a sec. Did the mic demon happen? Yes. So we have to have a term that accounts for that spatial change. So this is the spatial change term. And so the weird part is as you can see, this del up here is written as del dot v, and this one here is v dot del times v. And so what I was trying to figure out, because this dot product notation is not really a real dot product is the issue. Because so a dot product, again, let me just explain all of math. If you have two vectors, let's just do it with vectors. Okay, a dot product is a more specific version of something called an inner product, which is a way of, when we have vectors, like, actually, it's kind of funny, every single multiplication you do is actually a dot product, which is actually an inner product. Which people don't tell you, because if you're, like, a 3, and you want to just, like, if you're not 3, what time are you adding numbers in your life? 5? Yeah, probably 5. If you're like 5 and you're like, I want to multiply 2 times 1, you're not gonna be like, okay, project onto the space project your vector onto an infinite space of orthogonal bases. But yeah, everything multiplied is technically an inner product. So we want to basically be able to define multiplication for vectors. And if you just said like a vector like times another vector, we don't really know what that means, right? Like, okay, we have these two vectors, like there's an x and a y. This is our x, this is our y. Components in, it could be 5D, right? Like let's make it 4D. Okay, now we're in four-dimensional space, which you can't see, but just like pretend you can. Okay, don't worry about it. Everybody pretends. This will be called like, you know, x, not that. It'll be called I don't know, alpha. Okay. This is our 4D space, and we're trying to multiply these vectors. There are two ways you can do this. Well, actually, there are a lot of ways you can do this, because there are a lot of different definitions. But, well, we can't do this. I mean, okay, technically we can, but don't worry about it. If we want to dot these two vectors, wait, I can't imagine in 2 dimensions, then you just added 2 more. This is a sidebar. This is a sidebar about what a dot product is. So to do this, we take x1 times, like a regular times, x2 plus y1, y2 plus z1, z2 plus alpha 1, alpha 2. This is the definition of, let's call this A and B, of A dotted with B. Okay, so like keep that in mind. This is a mathematical thing that we just defined. Like I could make, you know, anything that just says like, okay, well, this weird shape, or here's a perfect example. Okay, here's a function, e to the negative t. I'm gonna do a funny multiplication sign like this and say cosine t, and this means the integral from 0 to tau of e to the negative t minus tau of cosine tau. We just made that shit up, okay? So it's okay. This is a real thing, by the way. That's a different thing, though. We don't need that. So, but the thing is, so del is an operator, right? And this del operator does something. That's a Cyrillic letter. Oh, V. That's V, right? I think that's one of the only Cyrillic letters. This del operator does something, right? And so del exists as a vector, and we said this earlier. Del exists as this vector where it's like all these partials. Like this is the big derivative, right? And it just keeps going down for however many dimensions you want to use it in. But the thing is that using del isn't like, it's not, when we take a dot product with del, it's not like you're taking a dot product, because if you think about this definition, right, this definition right here, if we were to say b dot a, and we were to just use this logic to calculate b dot a, right, we would get like x2, x1 plus y2, y1 plus dot dot dot. And because we're literally multiplying these, then these equal each other, right? So dot products are actually commutative. But then we have this question of, okay, so you have del dot v, which does not equal v dot del. And that is what I'm trying to figure out right now. Because the issue is that they don't teach us what del is, and they don't properly teach us what curl or divergence are either, because they teach us the parametric versions of them, but then you don't use those because they're parametric. So that's what we're. I might look at Paul's notes. My guy Paul probably has some good notes on it. Let's see, Paul's notes. Del operator. Also, congratulations, you just learned like all of multivariable, most of fluids 1, calc. Wait, he has a thing on curl and divergence. Let's go. Okay, wait a second. Next year I'm taking math, you just blew my mind. Well, that's good. Okay, let's go. Oh, thank God he gave a real definition of it. Oh my God, I love him. This guy is great, by the way. If you need, I learned nothing. I was painting eyelashes on a pink plastic otter. Clem, I love you. You're beautiful. Never change. yeah, I think actually the most fun part of teaching is trying to explain a concept to someone who just doesn't have any of the math involved. That's my favorite thing to do. Like, when I'm mulding over problems, I'll like go to my mom and I'll be like, Mom, I can't figure out why these two the one that I was telling her about. I was like, wait a second, this is important. Oh wait, if you join my Discord, Clem can post it in the Discord. Here, here's the Discord. Or you could just link it, either way. There's this, so if we think back to the no slip condition, right? There was this problem, before I took fluids, I was trying to understand my professor's notes. I was trying to like pre-game the class, you know what I mean? And so there's a question of if you have, so this boundary is fixed. This is our like fixed plate. And then we have another one that's moving at some speed v. The question is then, if you have two liquids of two different viscosities, how do they react? And so we know that the fluid up here, I'm going to draw the profile like this. Okay, so this is the start of our profile. The fluid up here has to have the speed v, right? And we know the fluid down here has to have the speed 0. But what he had drawn was like this, right? So we have one fluid that's like going to be sheared a certain amount, and the other fluid, like, it's actually, we're drawing. The other fluid shears more. And it depends on their relative viscosities and stuff. And I was molding so hard, because this is before I took fluids. So I didn't really understand, like, the whole, like, spatial versus time component of fluids. And so I was like, how is, because he said something like du dy equals 0. I don't remember what it was, but I was trying to decipher this. I was like, oh no, he said du dy 1 equals, what the I went to my mom. I was like, Mom, I don't understand this problem, but I like had to explain it to her. She was very good support about it. I love my mom. Because it was funny because the issue with I think the issue with being kind of verbose and like teaching stuff is like, if I actually don't understand something well, it is very hard for people who aren't like the professor to be like, you're wrong. Because I just know how to like convince myself into doing things. And so I'll just go off and I'll just be like, yep, this is what it is, and just keep going, and people will be like, oh, you're right. And I'm like, no, I was wrong that whole time. Please don't listen to me. When I'm like studying new things with people, you know, I tend to be sort of right on these streams, unless I'm like, I don't know what this is. Okay, curl. So we define curl as the z component. I remember this. This is what I remember this from. The z component sub y minus q sub z. So that's gonna be, oh yes, I do remember this. My professor, Professor Frankenstein, he said this. So yeah, so it's like dz dy minus dy dz plus dx d. Okay, so let's see. So we can just use it. And so if we say del cross f, that is defined as curl. Okay, let me write that down. Let's have a little notes. What language do I speak? Math. Exactly. Del cross f equals curl of f. So if we said f cross del, it would mean nothing. I'm kidding. It wouldn't mean nothing. Okay, so we say del equals this. That's what we knew what del is. So we can define curl using the following cross product. Okay, yeah. So it just so happens that like this cross product gives us this thing. Let's talk about the physical interpretation. Suppose that f is the velocity field of a flowing fluid. They tend to rotate about the axis that points in the direction of curl. Got him. Applied math. Then the fluid is called irrotational. Okay, yeah. Okay, the divergence is dp dx plus dq dy. So this is the, so really, like, I think the EE textbook that I read, when I shouldn't have read it, because it was a higher level EE textbook, but like, the example they kind of gave was like, okay, so this is kind of what we're trying to look for. This kind of behavior is like kind of trying what we're looking for in curl, and like this kind of behavior is what we're looking for in divergence. Like the tendency that from like for a field to like kind of pull away from itself in directions, versus a tendency for a field to like kind of come in and like rotate around. So that is defined as del dot f. So del dot f equals the divergence of f, which equals, here I'll write what they equal underneath them. This one equals dp dx dq dy. So we're saying the change of rate, the change of q, I'm gonna just say du dx, just so we stay a little consistent. Whoops, dv dy plus d. They use pqr in math, by the way, and we use uvw. I don't know why, because they hate us. Okay, this is equal to, it's like the, so we get rid of all the x's in our first term, and we say it's, I think it's z with respect to, yeah. So it's like v sub y, no, w sub y minus v sub w plus pz, so plus u sub z w, no, there we go, u sub z minus r z w sub x. Yes, get rid of the x's, that's the right thing to do. True. Okay, and then just trying to get this in my brain. It's better if I just memorize it or remember the mouth feel of it, you know? And then q, so v, there was a way, maybe I should look through my old multivariable. I keep going back to multivariable for this class, and like I kind of love it, but also it's kind of like scary because I took it more than a year ago. Okay, so we got that. That's the divergence. Okay, but what about like, what about the other way? What about the other one? What is v dot del called? Okay, so there's another one? Yeah, there's another one. Del dot v. It's not called anything? Oh, no. Okay, sometimes it's called nabla. I don't know. That's not... Well, let me just get the definition of it, and then... Oh! Okay, look at this proof. Guys, this it's 100 pixels big. This is so small. This is based. This is exactly what I need. Okay, here we go. So we're saying that we're trying to prove that this is a proof of like saying that del dot v is not equal to v dot del. Oh, because... Oh, that's crazy. Wait, that's so funny. So, it's like... Wait a second, this is the way that I'm thinking. It's like a gate. It's like a directional thing. You can put stuff because we define the divergence as this thing, if you do del only accepts things this way. So if you do this, then it spits out the function. If you put like an f into here, it'll spit out the function, you know, df dx plus df dy plus df dz. But if you try and put something into del the other way, this way, it just tacks on at the front. So if you put f here, it's going to be f times d dx plus f times... Wait, no. But it splits it up. Oh, no, yeah, because it's dot product. Lol. Like f sub x times that. F sub y times d dy plus f sub z times d dz. Is this vector fields? Yes. It's a very long, windy explanation to get... Just because we're working on this fluids problem about incompressible flow and probably Bernoulli's equation at some point, but we're trying to find the acceleration of this streamline here. And yeah, I'm just molding over this definition, but it makes sense because then... But it just sucks because then like the v, if you put a v at the end of it, it's not even like dotted, it's just tacked on there. Like, what the hell, man? That's so scuffed. Basically a whole 2-year physics course. Yeah. We're speedrunning. It's okay, really none of this matters. You just have to find it. So, okay, this is the fun part. Ready? Okay, so first we have to split up the components. So this is only in the x. So we basically say, whoop, those are 0. We don't have any more, we only have x. Now we just have to do dv dx. So u, so that's our v, vo. So sorry, I'm gonna plug in this because this is our thing. So vo, 1 plus r cubed over x cubed. That's just our x. And then we're gonna multiply that by dv dx, which we'll just pop up here first to solve for. Equals... That's v vector. I might have to split that up into 3. That's kind of janky. I mean, it doesn't really matter for us, so I'm just gonna... Okay, it's gonna be VO, 1 plus, and then the derivative of this with respect to x is gonna be, well, it's not gonna be 1, actually, I lied. It's gonna be r cubed. 1, x to the negative 4th times 1/3. Yeah. Is that right? If I integrate that. Yeah. Yeah. It's been a while. So that's our flow, I guess. That's our acceleration. You're only considering that, yeah. If you have the time and want to get a better understanding of what you derive, try this. Plot the acceleration as a function of position x. Indicate on your plot with a suitable label where, if any, the magnitude of acceleration is at a maximum, and indicate the magnitude of that acceleration. Ensure that your plot is properly formatted. Then think about whether the plot makes sense. Imagine a fluid particle moving along AB. As it approaches the front of the tennis ball, what happens to the velocity? Does this translate into what you see in the plot of acceleration? Let me multiply this out. It's a wacky, I was gonna say it's wacky that there's no negative, but there is a negative times negative 1. Okay, so we got VO squared, and then r cubed over x to the 3x to the 4th, and then wait, did I do that right? I think I did. Yeah. And then plus r to the 6th over 3x to the 7th. Okay. Let's plot it. Desmo's time. It's negative. Please be right. Please be right. Please look not dumb. When I have to do hard math, I end up just doing the math without knowing what I'm doing. Do you understand the math you're writing? Oh yeah, I do understand the math I'm writing. Like this? Well, that's why I went, oh, I don't know if this is right, because I understand what it's funny, I'm kind of the opposite. I understand what I'm doing with the math, but then I usually just mess up doing the math. Like, I know what to do. I know what it's supposed to look like, but then I just can't add like 2 and 3 together. Which I think is the better problem to have, because adding 2 and 3 together is a lot easier than fixing not knowing what you're writing. But yeah, we went through like a whole. I like to explain things to people who have like no background in whatever I'm explaining, because I think it forces you to really understand what you're doing. And yeah, we were doing that earlier. Oh, I can pull out an R cube. Let's pull out the R cubed. I'll just call this V sub O. Why not? Go to A. And then R cubes, this is gonna be 1 over x to the third, 3x to the third. What? Cannot index a number with a number at final be v. What? Oh, huh? Oh, it's an oops. Okay, I can't actually do that. Whoopsies. I thought that was yelling at me for that reason. Okay, and then plus r cubed, oops, divided by. This feels like doing a stereometry problem. You can see it but can't prove it. Do you often stream study? I stream, yeah, that's mostly what I stream. And then I also do other engineering projects and stuff. But it is a little hard because a lot of the projects that I'm working on now are sort of in that territory of like, I can't really stream them because it's not like it's NDA, but it's kind of in the space where it's like I don't really want that out there. Until summer, then he frolics and plays. Yeah, I do. I come out of my shell like a chrysalis in the summer. Let's see, plotting acceleration is at a maximum and indicate the magnitude. Well, okay, ours goes to infinity, so that would probably not be super right. Maybe. I mean, as it approaches the front of, so it accelerates like a lot here, and then it starts decelerating less, but it's still decelerating the whole time. It's very heavily decelerating, and then we go whoa, and then I guess we should probably plot VO. Let's do that. V sub O times 1 plus R. We can, oops, R cubed. I mean, this is literally just a regular partial derivative, so it should match up pretty well. Yeah, so we see that our velocity ends up and it trends to R, which makes sense. Summer can't come sooner. I want to play scary ghost game and force you to behold my demonic tricks. I'm so excited. I know I have a couple weeks left, unfortunately. I don't know what's happening over here. Doesn't really matter though. We only care about when time is, or when what is this? When x is positive. Because when it's not in there. Easy to mathematically derive something by following some steps. Well, yeah. I mean, it makes sense. We said that it would slow down as it gets closer because to the stagnation point, because it's a stagnation point, and stagnation points mean it's zero velocity. And then eventually it's got to stop accelerating because, you know, otherwise it would just keep going and then the ball would, you know, it would either go backwards or... All right. Wait, should we, we could do a, I might want to do a dimensional analysis? Ooh, Pog, maybe? I don't know if I can, but we might take a crack at one. Okay, this is the first, okay. Hurry up, get out of school sooner. Forcing myself through a self-love boot camp. I was supposed to be cherishing the time by myself more anyway. Aw, that's so nice. Okay, we got two. I don't know which one would be more fun. Let's take a look. Let's take a look-see. We got some cute little guys here. Okay, so this is dimensional analysis. It's a very different. Very different. It's basically like nothing like we were doing before, so sorry about that. Dimensional mice. Also, I'm not gonna be able to finish these problems because we didn't actually do the pie groups, but we talked about how to make them, so we can do the start of them. Okay, so we either have the boundary layer thickness delta on a smooth, flat plate in an incompressible flow without a pressure gradient depends on the free stream speed. That just went in one ear, out the other. Wait, did we ditch the last one or did you solve it? No, we solved it. We found the acceleration. We graphed it. I didn't plot the maximum because the maximum was infinity. Or the minimum, I guess. Maximum absolute value was infinity. This was our answer. And it makes sense. So as we can play around with stuff. So as our initial velocity increases, we would have to decelerate more, right? And then as our radius increases, so this is just like, is this increase or decrease if we think about our different variables? It's a good way to check. As our radius increases, we would have to decelerate more because we would essentially be having a smaller space, right, between like the ball and us. And then as our x increases, we're going to decelerate less because as we get closer and closer to the thing, our velocity is less and less, and so we're going to be decelerating less and less. So that makes sense. Is this physics and math both in one? This is fluid mechanics, so when you get to higher physics, yes, it's kind of like, I tend to stream in the math just because there isn't really categories for like, I can't stream in the fluid mechanics category, there isn't one. So I tend to stream in math when I'm doing stuff that is math heavy, because this is like pretty mathy. Okay, so we can choose either one of these. We can do, oh wait, no, sorry. This is two problems, get out of here. I thought it was choosing A or B out of there. Oh boy. Okay, so we can either do the boundary layer thickness or the wall shear stress. Both are cool. Wall shear stress seems like maybe a little easier. I hope you're going to continue next year. That would be of so much help. I'm totally going to do that. Yeah, I mean, and also, I am going to start doing my own lectures on stuff. I'm probably going to do lectures on like these higher level physics time, poggers, physics time, lectures on higher level engineering kind of stuff, because there's less of that out there. But I'm like, if you ever have like questions, I used to do this a lot more when there's one guy who would always come in and ask questions because we were like doing the same classes, but like if I routinely answer questions. So if you ever have questions and I'm streaming, like please be like, I need this help. Or you can DM me, I answer people's DMs. I also do tutor. I'm forever happy that one guy was like, I was so like out of luck trying to find a tutor that he was searching tutor on Twitch, and then I got him an A in his class and he got into med school, or a school so that he could get into med school, and I was like, yes, go. It was physics 3. You're born to be a teacher? Oh, thank you. What's the topic? I just joined now. We're gonna do some dimensional analysis. Yeah, we're about to start a new problem. Yeah, so I don't know, whichever one. I'm kind of feeling like I don't want to do boundary layer thickness, but just because I think I can do wall shear stress. Oh wait, they tell us the variables. Okay, good at chemistry. I'm okay at chemistry. It depends on the chem. I only had to take a little bit of chem. I'm not bad at chemistry. I actually probably can explain like Gibbs free energy and spontaneity and all that stuff probably better than the average person who took chem, but I know chem more for thermo and more for materials. You can proceed. All right, so we're trying to find, okay, our dependent variable is this this tau w, tau wall, and it's going to be a function of some other variables that we're gonna find. So it says that it's the distance from the leading edge of the body, x, the fluid density, rho, fluid viscosity, mu, and the upstream speed of the flow. So this is like a v or a u or whatever. Obtain the dimensionless groups and express the functional relationship between them. Okay, so we're gonna use something called the Buckingham pi theory to proceed with this. It's a funny little thing. Essentially, our point is if we wanted to experimentally determine a really good model for tau for any fluid, basically, right? That's the goal. You know, if we want to experimentally determine that, we're going to have to do a lot of experiments. And if we have this many variables, our experiments are going to start adding up really quickly. We're going to have 10 to the 4th experiments if we want to do 10 experiments per variable, which really isn't even, like, I mean, it's a decent amount of experience per variable, but like, you know, 10 is not huge either. We're gonna have 10 to the 4th, and that's a lot of experience. That would take like years maybe. So, you know, we want to reduce that, and so what we want to figure out is if any of these variables, if we change one of them, then we can actually be changing multiple of them, so that we have to change less variables in our experiment and still get a good model between the relationships. Okay, so we have our function. This is good. Sometimes, you know, you won't have this, right? If you're just trying to analyze data, you're gonna have to figure out, like, do you know what the variables mean? Yeah, so they give us these ones. This first one is the leading edge of the body. So if we look at, so a boundary layer is like this. So if we have our little guy here, we're gonna have a boundary of that fluid that's sort of going like this, and there's no fluid that's flowing across that. Hello, how are you? Oh my gosh, thank you for highlight. I'm doing well. Nobody ever redeems highlight. I think that might be the first time anyone redeemed highlight. So a boundary layer is, it depends on the thing. If you have two different fluids, you can maybe like see a boundary layer, right? Like this. Like if this was fluid 1 and this was fluid 2, you'd be able to visually see it if their fluids look different. But a boundary layer exists essentially in this idea that when we shear fluid, right, and we're getting to a steady state, there's going to be some part of this fluid that has a velocity like this. Like we're creating a velocity profile essentially with our, and this isn't a thin gap. I drew it kind of like a thin gap. It's not a thin gap because if there were a thin gap, it would be a linear velocity profile, but we'll make it a little bit thicker like that. And so we basically just have a point where our it's kind of like a streamline. So that's what it is. So it's saying the leading edge of that, of the body, which I would assume is this. Ours is probably going the other way, but yeah, it's not really leading in this, if time is positive this way, but. And then we have the fluid density, that's just density, fluid viscosity, that is how kind of like sticky the fluid is, and then the free stream speed of the flow is just the velocity of the flow. So we have to find the relationships between these. So our second step is to make a, what is it called? It's called a dimensional matrix. And so we want to express our parameters in terms of their dimensions. And just to kind of talk about dimensions, because you probably don't, maybe you've heard of it. So a dimension is not a unit. Units are not dimensions. They are the kind of like the most basic form of measurement is a dimension. It is the true length of something, or the true time it takes something to happen. So they're always perfect and accurate. And we can express every unit that we have, like for example, for a Newton, in terms of these very basic dimensions, right? So Newton is a kilogram meters meter per second squared, right? And so this would be a mass times a length over time squared. So that's how we write a unit as dimensions. So these are the dimensions of force, right? So what we're going to say is we're going to say that all of these different variables can be expressed in terms of these basic dimensions. Please explain dimensionless stuff. I hate those. This is like how people get properties like Reynolds numbers or Mach numbers, which are based off of those are dimensionless numbers that like exist. And you say, well, if the Mach number is less than 0.3, then it's a compressible flow, and that's how they do that. This is temperature, by the way. I don't know why he wrote it as theta, but I guess he wrote it as theta. Just gonna do the way my professor does it. All right, so we write our parameters down here. So we've got our x leading boundary here. We've got our density, our viscosity, and our velocity. So what we're going to do is we're going to say, okay, what are these units, and what are their relationships with each other? So for x is probably our easiest one. X is just going to be a length, and we know that x is like length, like that. So we're going to put a 1. So these numbers that I'm writing here are going to be exponents. So it's 0, like mass to the 0th power, time to the 0th power, temperature to the 0th power. Simple. For density, we have kilogram. I mean, if we do it in units, it's like kilograms per meters cubed. So that would be kilograms per meters cubed. So it's on the bottom, so we put a negative. None of these, well, viscosity could be a function of temperature, but some of this is spread out of Greek letters, so they reuse it. Oh my god, yeah, rows, I think P is the biggest culprit. P can be so many things. P's, you just gotta know contextually, unfortunately. The other easy one is gonna be this little friend right here. That is velocity, so that's gonna be meters per second. And then we have to do viscosity. So viscosity is, the way that I can think about it is we use Newton's Newton's law of viscosity. That is the definition of viscosity right here. You could also just look up the units for viscosity, but like if we wanted to prove it. So this is a force, so we're saying it's force over, and this is length. Do I want to say that? That is, well, it's not like that. It would be, whoops. Let me check that I'm doing that right. I don't want to do that, actually. Fuck it, we ball. I don't want to get it wrong, because if I get it wrong, then it's like, we're screwed for the rest of the problem. Let's see, viscosity is units of, or, oh wait, what? Oh, it's, oh, no, we're chilling, wait, bring it back. This is tau. Tau is not a force, okay? Tau is a force over area. Force over area is our, that, and then our rate of shear deformation is gonna be like shear per, would that be shear per, let me see. Wait, I want to see what shear deformation. I'm guessing it's shear per second units. Oh god. Nope, that's shear strain. Now we're in mechanics of materials. I think it is. Oh, nobody likes giving me units for that. What are the units of shear deformation? Well, that is, oh, I guess it's just 1/1, and that's force over area, but that's not what it is though. It's the thing. Let me see. Viscosity is Newton seconds over meters squared. Does that make sense? Let's see. Let's see what we get. So this would be newtons over meters squared, which is kg meters per second squared, meters squared. But this is a pressure though. That's a pressure. It's not tau though. But like du dy, this would be meters over meters. Okay, we're just gonna get the right answer and use the units because those units are real units. It is not that, it is Newton seconds per meter squared, which would give us kg meters per second squared times seconds over this. Get rid of that. Over meters squared. Get rid of that. Equals kg second meters? Change game. Wait, I don't know if... Oh, wait, you're using an exclamation point? I have redeems, you forgot. I'm affiliate, baby. Oh, Pascal seconds, yeah. Which is... A Pascal second, I think, is a kg meter... Yeah, kg per meter second. Weird thing, but that's what it is. So kg 1 per meter second. All right, well, we did all that. It's a reference. So tau equals F over area, mass times acceleration over area, mass times... Ooh, would you say this is dimensionless calculation if this makes sense? Davey doesn't know his own fan-based jokes. The Davey heads? So we haven't done the dimensionless part yet. We haven't gotten there yet. We're just trying to figure out what the units are. So essentially what we're going to end up doing is like combining stuff together so that their units all cancel out. And we're gonna do that in a sec. First, we have to figure out how many we can have, and I'm not gonna do this out, but essentially what we do is we're trying to find the maximum number of linearly independent variables that exist here. So all of these, I'm gonna use some linear algebra, okay? Bear with me. So this is sort of like our basis, these vectors, okay? So each of these values is made up of each of these variables, right? We could make up a variable called like a smiley face, and we could say that it equals like 3, 4, 2, 1. We could say whatever. I love when things cancel out. It's so satisfying. It's gonna cancel out. We're gonna get there. Right, and like smiley face is just as valid as a variable as any of these variables. We're just saying that there's some, linear combination of these exponents that exist to this. So this is our basis, and it's really like an infinite basis, but we're not gonna worry about that. We're trying to figure out which one of these, how many of these are linearly independent, so that we can figure out how big our group should be. So the way that we do that is by finding like the rank of a matrix. Why use Greek letters when you have smiley face? That's what I'm saying. Potato, 1 potato plus 1 potato equals 2 potatoes. Always. That's what my trig teacher said, and I will forever remember her for it, because I was like, you know what? Yeah, the derivative of potato with respect to potato is going to be 1. Never going to forget that. Just don't worry if it's like cosine of, no, potatoes. Don't worry about it. So we want to find, the maximum number of linearly independent. And the way we can do that is by taking a determinant of a matrix. So we want to find the biggest matrix, essentially, with rows and columns. It has to be a square matrix. And we're not going to have 4 rows, because if we take the determinant, these are going to give us zeros. So we're going to have to find a 3x3. And I don't really want to go through, because you can do like any of these. You can do like this one, or this one, or this one, or this one. Like you can do any combination of these to get matrices. I'm just gonna say, for time purposes, we're gonna say that the rank is 3. It's usually 3. When you have, like, if there was temperature here, it would usually be 4. So it's plausible. We're trying to find we're trying to find the determinant that doesn't equal 0. And that's how you have linearly independent vectors. We're going to say that it equals rank 3. So then what we're going to do is we're going to take our parameters and we're going to try and group them together, because what we're trying to do is we're trying to say, we're trying to create a group that's like a pi group, right? Or like our number, like kind of like a Mach number or like a constant. And we're going to put that together with another constant and another constant. And then the thing we're trying to solve for is going to be our last thing. So we're trying to group everything, you know, together with that. All right, so now we have to figure out how we want to group these. And you can pick anything, kind of, which is weird. Like, so part of this like process, the dimensionless process, is like, is knowledge, is intuition that I don't have because I started doing this today. So, you know, go figure. But you can use like a couple different basic groups for fluids, at least. So the ones that we use are like fluid properties. We say like flow field. So we're gonna write out our variables and we're gonna pick from one from each of these. Geometry of the problem. This is so we don't really get like overlapping units. Like if you chose x and velocity to be like in your or like let's say you had another dimension here, like that was like radius or something, and you choose x and radius, then it wouldn't really work out. I mean, you could choose it, but it wouldn't work out well. Because you can make pi groups that exist that are valid, but they just don't really do anything for you. There's freedom of choice, at least that's smart, yeah. Yeah, you do get to choose. I mean, they're like, it just depends on, so like this process is kind of used for like sorting through data. And so if you don't have data, like this problem, we're not given any data, it's just like 2 sentences. So we'd have to see, you know, we'd have to get some data to actually see if our pi groups were gonna help us out at all, but we don't have that, so. All right, so for our fluid properties, that's gonna be our density and our viscosity. Our flow field, that's gonna be our U, and then our X is gonna be our geometry. So we get to choose 3 because we have rank 3. And so we're gonna choose, we have to choose U and X, and then we're gonna choose density because unless we're at a micro level, inertia is gonna dictate fluid properties much more than the shear at the walls is. I mean, it doesn't have to be an inviscid flow for that to be true. We still like have shear, but it's just not as there. Oh, thank you for the follow. Oh, everybody. Gold and Caleb C. She? No. Well, kind of she, but like sure, if you were to pronounce it with pinyin pronunciation. All right, so then we end up with groups. So we take our group, we say U, X, P, or rho, and then we kind of group them with our other variables. So it would be U, X, P, and... Oh no, I didn't put tau in here. Fuck. Tau's also here. It's okay, don't worry about it. We have to say tau. Tau is force over area. Did we do that one? That's newtons over... Well, no. Wait. Yes, it's pressure. So newtons over meters squared equals kg meters per second squared over meters squared. All right. Kg over second squared meters. Got a little wacky at the end there. Okay. So that would be kg 1 over second squared meters. I also wrote an m there. There we go. Yeah, because tau is one of our... We can't choose tau, but it's there. Okay, don't worry about it. So our groups are U, X, P, and tau. And then U, X, rho... Sorry, not P. Rho and... What was our other one? Viscosity. Oh, sparkle on! Oh my gosh, it's been so long since I sparkled in the sun. It's so beautiful. It's so lovely out here. Thank you. Well, and that's all we can go. That's all we can go to. Yay, sparkles. That's all I got. We made some pi groups. Those are our pi groups, and then we have to test to see if those are good, and we find some exponents, and they'll cancel out or whatever. But that's the basic idea. And I mean, you would do the same thing for this, right? So like, in this case, we would still have the. So we're trying to solve for the shear here. That's our tau. And in the other case, we would be finding the delta. So that's like the delta here is delta. But we're not finding delta, we're finding tau. This one is maybe slightly easier because it, I'm crashing slightly. Because this is just gonna be an L, but like our tau is gonna be like, not just a one-dimensional thing. Don't worry about it. Okay, let's, well, we got time. I got some time. I have a meeting at 2. I have to go at 2, but, it's exciting that there are so many people here who love fluid dynamics. Or maybe don't love it, maybe they're just here. And that's also fair. I see you, and it's awesome that you're here. Okay, let's take a crack at it. Let's go for it. I'm seeing a lot of words, and that is either good or bad. So that's great. I love that. I love it when I see a lot of words. I don't love it. Okay. All right, we get some info. I like the info that I'm seeing at the beginning here. I could transfer my 999 starbits from Super Mario Galaxy World save file to Twitch. Oh, I might make redeems worth less. I do love fluid dynamics, but mostly topology. Ooh, I have not gotten to do topology. I probably won't get to do topology. I'm thinking over the summer of doing some vector calculus. Or vector analysis, sorry. Vector calculus, very different. Because I just love vectors so much. I love vectors, I love tensors. I love matrices, all that stuff. Alright, okay, we get laminar, fully developed, pressure-driven flow. Okay. So dpdx is not 0, not 0. The velocity profile is given by the expression, bam, where the pressure gradient can be treated as a constant. It does not change in the z direction and is actually equal to delta p over L, where L is the pipe length. Fully developed flow means that the velocity profile no longer changes in the direction of motion. So that's dz, dwdz. Have I tried multivariable? Yeah, I took multivariable. I like you gotta use multivariable to do all this stuff. It's fun. Using continuity and Navier-Stokes in cylindrical coordinates, derive the expression for the velocity field provided. All right, let's draw some stuff. I think that's a good start. We need a schematic. This is a chonky boy. Schematic. We're only gonna be able to start this, unfortunately, but. Okay, big pipe. What would be the best way to draw this? Maybe let's draw this sort of at an angle here. You can see a little bit better. All right, and we have a coordinate system. Let's do this. Here's our coordinate system. We're not going to be using Bernoulli's, so we don't need a streamline, but, you know, it's going to go through the center, and then we'll say R goes down. I don't know, whatever. Cool. And then, like, theta is out, like that. All right, coordinate system, good. So, laminar, fully developed, pressure-driven flow. So, laminar is for... Okay, let's make some assumptions. We need to assume Newtonian for Navier-Stokes, even though we don't have to... I guess I probably should assume steady. Fully developed, I mean, it's full, yeah. We'll say steady, just in case. We're gonna say fully developed. I don't really need to state that, but it's whatever. We're also gonna say Newtonian. That's for later, though. We won't. It's like the Mickey Mouse. We'll use this trick later. Okay. Let's just do continuity. Let's start with continuity. Always a good place to start. Really the only place you can start. Cons of mass. And that is going to be our 0 equals d rho by dt plus our, this is divergence dot rho. Okay, is it compressible or not? It doesn't say that it isn't compressible. So I guess we just leave it in there, although it is steady, so this is not going to be... Oh wait, it doesn't matter if it's... would it matter? It doesn't matter. No, it doesn't matter. Wait, maybe it does. Oh, yeah, it would matter, because if our rho is a function of... if our rho is a function of... I might be thinking about it too hard. Fully developed pressure-driven flow. Is it a liquid? Circular pipe. Doesn't say that it's a liquid necessarily. Oh, we're doing okay, we're looking for parabolic behavior. Oh, also, I don't need to draw it like this. I can draw it like this. If we're looking for parabolic behavior, I don't need to care about... We're not going to be caring about anything but this. Guess I didn't really look at the equation. I was like, it's like equation's there. I'm gonna solve for it, so I don't really need to look at it right now. It's the trap. That's how they get you. Okay, R. All right. I mean, I guess we could just say curl. Not curl. Divergence. Is 0. I'll leave the rho in there though. We'll say this. We'll say rho x du dx plus rho y dv dy plus rho z d. Oh wait, we're not in that direction. Oh, it's cylindrical coordinates. Wait a second, I need to look up what the cylindrical coordinate version of continuity is. It's not the same thing. I'm in head loss. Why am I all the way down in head loss? Okay, Continuity. Cylindrical coordinate system, here we go. Oh no, oh no. Wait, is that? I'm gonna leave it without they like say divide by r. It's not this though. Ew. Okay, I'm just gonna set this up and then we'll take a look at it. We'll try to cancel some stuff out maybe, and then I gotta scoop. Okay, so we have d r rho vr over dr plus d rho v theta over d theta plus r d rho vz over dz plus r dp dt. Okay, so this is 0. Now we said that in the direction of flow, it's so the d dz vz dz is going to be 0 because we said that it's fully developed. So in the direction it's moving, it's not gonna go more. So now we have dr rho d. Well, we can set these equal to each other. So we have dr. Well, is r? No, we'll leave it. Vr over dr equals negative d rho v theta over d theta. So we got that, and we'll probably have to sub some stuff into Navier-Stokes and figure out some more stuff there. Yeah, it's definitely a little bit of a longer problem. I think I'm probably gonna do this on stream. When you do the dimensionless equation, isn't it smart to check if they cancel out? Oh, I didn't finish it because we actually didn't. There's more to that process, but we just haven't gotten that far in lecture. So I just did as far as we had done. You'll have to. I'm gonna talk about. Well, so I'm doing fluids. I'm gonna write my own lectures for it over the summer. So if you're interested in like the actual better version of me teaching it instead of like the speedrun version that I do, I tend to do like semi-abridged versions on stream, or not in turn. I'm not assuming that people have prerequisites essentially. I like this chapter because you do quantum chromodynamics next. Ooh, that sounds cool. My brother does quantum chemistry. How do I make sure I do have Discord? Yes. Yeah, and I have a VODs channel. My VODs channel is woefully backlogged right now. So if you're looking for VODs of these streams, they probably won't be up for a little bit, but they are on Twitch. But I mean, if anybody wants to watch them, or if there's one that you're like, oh, I want to see this or whatever, I can upload them unlisted. I just have to like edit out the demon mic, so it takes me a while to go through all of them and do that. That's why I don't upload them just instantly after I do stream. Also, I'm trying to upload them in chronological order to my best of my ability. So, yeah, I will be back on Friday, probably doing this and also maybe a little bit of Fourier series. That should be fun, I say, as I stare at my 12 integrals I need to do for those. Need to go to bed. Have physics test tomorrow. This seems like a lovely community. Oh my gosh, thank you so much. Good luck on your physics test. Should leave the demon mic in, free jump scare. I left it in for one of mine and I felt so bad that I had to put sections in the video that said like demon mic. Do you have a YouTube channel? Maybe I could learn more from. I do have a YouTube channel. Oh my gosh, everyone being so excited about stuff. You guys are so niceies. Let me grab it. It is probably the same. It's damie VTuber. It's the same as my handle. You guys are so sweet. Thank you so much for liking my stuff. Teehee. There's what's up there? Lots of multivariable stuff. There's all my statics is uploaded all now. Statics is like easy. Oh my gosh. Linear algebra is up there. Multivariables up there. I don't know. I don't remember. I don't know if anybody like who's been here remembers, but like I took Physics 3 and I don't think I streamed anything for Physics 3. I was trying to like give somebody like electrodynamics stuff and I was like, where are my VODs for electrodynamics? There's just none. I don't know why. I like scorched earth my Physics 3. I didn't really like taking it. It was harder for me, but like I'm surprised I didn't stream it at all. But I was like hella burnt out last year, so. All right, I'm going to call it. We have enough. Should we raid? Who's alive? I'll raid somebody. We got enough people to raid. Oh my gosh, we can raid in Stucky. Let's go, dude. Stucky's awesome. Okay, yeah, we're raiding in Stucky. Stucky does math, and they are so swag, and they raided me, and now I get to raid them, and that's awesome. So I think everybody should go. They might be doing Leap, which is Lean, which is like a math proof type IDE. Okay, I'm gonna be back on Friday. I need to be. I'll probably stream a little bit earlier now that I know that like. Wait, no, I can't. I have to stream at like 12. Okay, I usually stream a little bit later. I normally stream like at 1 p.m. PST, but I ping in the stream. All right, I will see you guys then. Let's go give Stucky a great raid. Bye, everybody. I'll see you then.